Today we're going to talk about integration and what an integral is. So really, the simplest way to describe what an integral is that it's the area between some curve and the horizontal axis. So if we look at this graph here, the top graph, where we have y on the vertical axis, x on the horizontal axis, and we have some function, say f of x. Well, there are times when we're going to be interested in determining the area that exists between a and b and f of x and the horizontal axis. So we want to determine all of this area right in here. So how can we do that? Well, the first thing we're going to look at is how we can estimate this area. So we want to conduct an estimation, and so a way we can estimate is by drawing a bunch of rectangles underneath this curve. Okay, so we have a bunch of rectangles, and let's say that the width of each rectangle is delta x. And we have a finite number of rectangles to conduct our estimation, and so really we've split the x-axis into some intervals here, and we'll say this is the value x sub 1, this is the value x sub 2, all the way down to x sub n. Okay, so we have x sub n number of intervals that give us all these rectangles. So how do I determine the area of each rectangle? Well, we all know how to calculate the area of rectangles, and that is to take the length times the width. So what is the width of some arbitrary rectangle? Well, it's delta x, okay? Delta x. Now what's the height of the rectangle? Well, each rectangle has a different height, but if we're looking at this rectangle right here, well, the height can be calculated by taking f of x sub 1. F of x sub 1 corresponds to the height of this rectangle. So that gives us an approximate area for one of the rectangles, and now we want to do it for all the rectangles, so eventually we just want to sum them all together. So what I'm going to do for my approximate area is, instead of one rectangle, we're going to look at in rectangles. So I'm going to take f of x sub I, being the ith rectangle, times it by delta x, the width of the rectangle, and we're going to sum those all together. So notationally, I'm going to take the sum from I equals 1 to n, however many rectangles I have to approximate this area. So the sum of f of x sub I times delta x, that gives me an approximation for the area between f of x and the horizontal axis. All right, but I don't want an approximation. I don't want an estimate. I want a definite answer, or an exact answer, for the area between this curve and the horizontal axis. So what do? Well, I'm going to apply this thing called the limit again. And I say again because we did this when we talked about derivatives. So what I notice is that if I have more rectangles, then I can get a better approximation. So by taking the limit as n approaches infinity of this sum, I equals 1 to n of f of x sub I times delta x, if I take this limit, that's going to give me an exact area that exists between this curve and the horizontal axis. So we look at this and we say, great, that looks good, but man, how do I compute this? Well, of course we can do it, but it takes a little bit of math to do that. And fortunately, what some people realized when they were developing calculus is that there's an inverse relationship that exists between integration and differentiation. Okay, so now we're going to talk through the fundamental theorem of calculus, which allows us to calculate this limit, essentially. So fundamental theorem of calculus. So before we talk about that, notationally there's another way we can describe this area, and that is the area is equal to the integral from a to b of f of x dx. And really, this is just a nice way to describe this. These things equal the same thing, which is the area between f of x and the horizontal axis. So we're going to work with this notation with the fundamental theorem of calculus, which is going to provide the link that allows us to easily calculate this area. Okay, so fundamental theorem of calculus, it's broken down into two parts. So for part one, what part one states is that if we have the function g of x equals the integral from a to x of f of t dt, then g prime of x equals f of x. Okay, so we're going to talk about this a little bit, but this is very important in providing the link between differentiation and integration. Okay, so with this in mind, let's talk about where this comes from. Well, let's look and see what g of x is, and notice where the independent variable lies. The independent variable lies in what is called the limit of integration, right, x. So what does this expression mean? This expression, the integral from a to x of f of t dt, if this is our curve f of t, this function means it's given us the area between f of t and the horizontal axis to some point x. So this function g of x, when we input this value x, our output is the area between f of t and the horizontal axis. Okay? So where does this come from? All right, where does this g prime of x equals f of x come from? Well, if we remember what a derivative is an instantaneous rate of change. So if this function represents the area so far under the curve to point x, well, then this rate of change is the amount of area being added at point x. Okay, so how do we get that? How do we determine that? Well, let's think about if we have a little slice that we are adding into this area, and this slice goes to the point x plus h. Okay? Well, if I'm going to determine the height of this rectangle, again using this concept of approximating rectangles here that we used before, well, the height of this rectangle can be determined by this point f of x. Okay? So, how do we determine this g prime of x? Well, we are going to say then that g prime of x is roughly equal to the amount of area we're adding into this, which would be defined as f of, we'll say x plus h minus f of x divided by x plus h minus x. And notice these x's cancel out. Okay, so this has given us the amount of rectangle that's being added. Okay, so what do we realize about this? Well, this looks like how we were calculating an average rate of change. So to make this go from an estimate to an exact solution, then g prime of x is just simply equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this, we notice, is the limit definition of a derivative. Okay, so then g prime of x must just equal then f of x. So that's the fundamental theorem of calculus part 1. So fundamental theorem of calculus part 2 gives us that, we'll go right down here. Part 2 gives us that the integral from a to b of f of t dt is just simply equal to what we denote as big F of B minus big F of A, which big F represents what we call the antiderivative of the function f of x. So if we think back to differentiation, remember that if we have the function f of x equals x to the n, well, to differentiate that, to get f prime of x, we just have times x to the n minus 1. Well, how do I go from f prime of x back to f of x? Well, we take what's called the antiderivative, which is what's represented by big F. So if we have f prime of x equals n to the x times n times x to the n minus 1, then f of x equals x to the n plus 1 over n plus 1 plus c, where c is this constant of integration, because the derivative of a constant is just 0, and so if we're working backwards, then we have to have this constant of integration. So this is then how we can get to an exact answer for the area between f of x and the horizontal axis.